we have a pulley. It has some mass and radius. I don't know, we usually know these, and has a mass. And you have a string attached to it, wrapped around it with the weight hanging down here. We'll use small m for this mass, capital M for that one. And you hold it, then you let it go. Well, if you let it go, what will happen? That pulley actually will start to spin and the weight will drop. So the weight will travel down with some velocity we'll call it v. The pulley is going to spin counterclockwise, or clockwise, not counterclockwise. Well, let's look at this piece here, this mass. So I'm going to do a free body diagram for the mass here, the little mass that you hung there. It has a weight down, which is mass times gravity. It has the tension in the cable pulling upward. And which way is it moving? If it's moving down, if we assume this is going to move down, then my equation I can write mg, the mass times gravity, the weight, minus the tension, equals the mass of that times the acceleration. And we normally know what the mass of this one, so I only have really two unknowns, t and a. I need a second equation. I need to find another equation because I have two unknowns. Let's assume the mass, let's put some numbers here just to show it's only, so the mass of this, we'll say it's 1 kilogram. Let's say the mass of this is 2 kilogram. Let's say R equals, I don't know, 10 centimeters, the radius. So when I put these numbers in, I know the mass is 1 kilogram. 1 times 9.8, that's 9.8 minus T equals what? 1 times A. How many unknowns do you see there? 2, right? One equation by 2 unknowns, none of us can solve it. Okay, let's look at the pulley. So that's this weight. Here's the pulley. We got the tension pulling in this direction, the cable, the string. We got the radius here. We know torque equals what? We did that last class. Inertia times what? Alpha. The torque is the force pulling down times that distance. Well, what is the force pulling down? Isn't that the tension in the string? What the string is pulling on me? So T times R. Inertia. Let's assume that's a solid disk. If it's a solid disk, the inertia for that is 1/2 mr squared. From the table. I have extra copies in my office for these inertias if you need them. 1/2 mr squared. It's in the book there. I know not all of you have the book, so I can get you a copy of that. and times alpha. Well, alpha doesn't help me because this equation has T and A in it. This has now T and alpha. Well, we know A equals what? R times alpha, isn't it? Which means alpha equals what? A over R. So if I replace alpha with A over R, I can get my other equation. Let's plug in the numbers. The tension is unknown. R is what? For that example, 10 centimeter, which is 0.1 meter, equals 1/2 the mass which is of the pulley, that's 2 kilogram, times R 0.1 squared, times A divided by R, which is 0.1. If I did the math correctly, just coincidence here, it says the tension mathematically equals to A. 1/2 cancels this, the 0.1 cancels one of these. So that's my second equation. Go to the first equation now and plug them in. 9.8 minus, in place of T, let's put A, equals 1A. 9.8 equals 2A. Can we solve for A? 4.9 meters per second squared. Can I find the tension in the cable? 4.9 Newton. So notice I use torque here to get the second equation. Torque is inertia times alpha. I know what inertia, I can tell you what alpha is. And torque for this is going to be whatever the force times that distance, and the force is the tension of the cable times the distance, which is the radius of that pulley there. And that's where the second equation came from. We'll try another one. We did in the lab this experiment. You probably did that at night. We had a table on it. We put the track, and we had a weight sitting on it. It goes over a pulley here, and you dangle some little weight there, and the thing will slide down. Did you guys do that for the night, the lab? Yeah. And you can measure the acceleration, all the stuff on the device we have there. Now, the one in the lab we have, the mass of this is roughly 0.5 kilogram, give and take kilograms. It's 500 grams. So it's 501, 502, 498, but around 500 grams. The string passes over a disc-shaped pulley. The one in the lab actually is not a disc, so the pulley is disc. So we have a disc pulley, and the reason we use the word disc here, why? Well, if it was a hoop, it's also circular, but the reason the word disc there, because inertia for that is 1/2 mr squared. So the word disc used to tell you what the inertia is. Because it could be in a loop, like a bicycle wheel, we have a spoke through it. That's not a disc, that's not a solid one. That's a hoop, you know? And the inertia for that's mr squared instead of 1/2. Different inertia for that. Let's assume the pulley has a mass. That's the pulley here. The mass of the pulley is 0.08 kilogram, really light one, 80 grams. and has a radius of 0.012. So now I can calculate the inertia immediately. 1/2 the mass 0.08 times 0.012 squared. So we know what the inertia for that pulley. Which is a small number, 0.00000012345 or 5.76 times 10 to the negative 6. That's why in the lab, if you remember last semester when we did these, we neglected the pulley because the inertia is so small. It wasn't worth mentioning on these devices. But if you have a big heavy pulley there, you can't ignore it. So we took a little weight here, we'll say, I don't know, what are we going to use here? Let's say 100 grams. That's a lot. We used to hang 10 grams. We'll put 100 grams here on this end and to watch it slide there. Now I'm going to show you what we did last semester. I'm going to show you what we're going to do today. Last semester we neglected the pulley. In Physics 1 you never dealt with the inertia. The way we approach that, if you recall, so this is in Physics 1. We did it with no inertia. So we looked at this one moving down. We said, well, we got the weight down, which is mass times gravity. The mass is 0.1. Gravity is 9.8. That's 0.98. We got the string pulling up there. We'll call it T, tension. And this was moving down. The equation for that, 0.98 minus T, because you're moving down, that means this is bigger than that, equals the mass, which is 0.1 times the acceleration. Is that how you did it in Physics 1? He might have used up positive, down is negative. It doesn't change anything. Still the same. The other one, the 0.5 kilogram, has a weight down, which is 4.9 Newton, has the normal force pushing upward of 4.9 Newton because it stayed on the track, it never moved up and down, and you get the string pulling in this direction. And which way was it moving? It was moving to the right. That's the direction it was moving. Newton's second law says if you move in the net force in that direction, which is only the tension, equals the mass times the acceleration. And there's the two equations that we had. So now we have two equations by two unknowns. Plug them in. 0.5a, 0.1a, 0.98 equals what? 0.6a. Can we get the acceleration? 0.98 divided by 0.6, which is 1.63. And if you know the acceleration, you know what the tension in the cable. The tension in the cable is 0.5 times A, 0.82. That's how we did it last semester in Physics 1. Let's see what physics 2 is going to approach it. Same problem, physics 2 now. With inertia. This is that 0.5 kilogram on the top. .1 kilogram, you get the weight down, which is 0.98. We get T1 here, tension pulling upward. We get this tension. I'm going to call it T2. I'm not sure if they are equal or not. We'll see if they are. You get the pulley there. And let's see what's going to happen. Let's look at this one. This is going to the right, so that didn't change. Newton's second law says the net force equals mass times acceleration. The net force is T2, the mass is 0.5, the acceleration is A. So that equation is still the same. This one, it's moving down. So it's 0.98 minus T1 equals the mass, which is 0.1 times the acceleration. Now notice I get how many equations? 2 equations by how many unknowns? 3 unknowns, right? I get T1, I get T2, and I get A. I need the third equation. That's where the pulley comes in. Torque equals what? Inertia times alpha. The pulley now. Now, just let's look at these. T2 is going around this way, T1 is pulling this way. This is going to make it spin which way? Counterclockwise, right? This one's going to make it spin which way? Clockwise. So the torque is actually, torque is going to be the force times the distance. Well, it's T1 is going to make it spin counterclockwise. So T1 times R minus T2 times R. That's the torque. Inertia, I calculated the inertia 2 minutes ago, right? What was the inertia here? A small number. See that one? We did calculate that. 5.76 times 10 to the negative 6 times alpha. I don't want to use alpha. I'm going to use A. Well, alpha is what? A over R. That's what alpha is. And what was my R here for this? For the pulley, R was what? 0.012? Plug it in. 0.012 T1 minus 0.012 T2 equals 5.76 times 10 to the negative 6 times A over 0.012. 0.012 T1 minus 0.012 T2 equals 5.76 EE to the negative 6 divided by 0.012. 4.8 times 10 to the negative 4 times A. I could clean this one a little bit more. I can take it and divide every term by 0.012. Just to make these numbers cleaner. And if you divide it by 0.012, what are you going to have? T1 minus T2 equals 0.04a. And that's my third equation. Equation 3. T2 equals 0.5a. That's equation 2. And 0.98 minus T1 equals 0.1a. That's equation 1, or well, this is 1, I think, and that's 2, the way I derived them. So these are my 3 equations by 3 unknowns. So now really I can't ignore the Pulley there. Your answer might not be much of a difference than the previous one because the thing was small, the Pulley. Didn't have much of a mass, but let's see. If we do some substitution here, notice if you take this equation and solve it for A. Solve it for T1, not A. Solve it for T1. You have negative T1 equals 0.1A minus 0.98. Divide by minus 1 to get rid of that. T1 equals negative 0.1A plus 0.98. Now grab this equation. In place of T1, let's put this number. In place of T2, let's put what? 0.5A equals 0.04A. How many unknowns do you see there? 1 unknown, right? 0.1A minus 0.5A, negative 0.4A plus 0.98 equals 0.04A. Move this one to this side, 0.98 equals 0.44A. And what is A equal to? .23. Can we get what T1, T2? T2 equals 0.5 times that number, 1.11. T1 from this one, negative 0.1 times A. We know what A is, so negative 0.223 plus 0.98, 0.757. How far are we from the old-fashioned way of doing it? From physics 1. My acceleration, physics 1, was what? 1.63. And now the acceleration is what? 2.23. We assume these guys are equal, a value of 0.82. Notice a little bit off. We neglected the Pulley completely. We couldn't bring it because we don't know what inertia is. We don't know what the other stuff is. But that's really what's going to happen there. So that's the difference between the way we did in physics 1 and the way it's done now in physics 2.